The next
Good morning, sir. I am
present.
ready to present.
Okay, the presentation named Design and Parametric Investigations of Permanent Magnet Adhesion Mechanism for Robots Climbing on Reinforced Concrete Walls. Please.
Thank you. Good morning, sir. My name is Vijayagopala, and today I am here to present on behalf of my co-authors and corresponding authors regarding the paper Design and Parametric Investigation of Permanent Magnet Adhesion Mechanisms for robots, for wall climbing robots on concrete walls. So, in this paper, we will be proposing about various designs. We'll be talking about various designs of magnetic adhesion mechanisms, which could be used on concrete surfaces. And also, we will be investigating about what each design provides us, what is the adhesion force given, and how much payload it can carry. So before that, why is this research important? Like, why is this magnetic adhesion important for us? So for that, to answer that, we are involving robots in our day-to-day works, and we are inclining towards robots for various automation tasks. And Industry 4.0 is not very much far away. We are already involved in it, and a lot of works is being done using robots. And variety of tasks being performed by robots also, but there is one particular field where robots are still not being used, and there the risk for human life is very much high, and that is which is when humans go for inspection tasks on a dam, panic attack or vertigo sensations like that. So there's a lot of risk involved in that. Not only dam inspections, even high-rise buildings. Today we are constructing a lot of involved in an inspection task for that. His life is at stake. And also, if you can see, we have a lot of bridges on in India. If you see, especially, we have the one which you're seeing here is a Rajahmundry bridge situated in Andhra Pradesh in India. This bridge right now, now that area is currently flooded. So, and when the flood goes off, still the water will be the same way as you're seeing in the picture. It's highly risky. There's not just one bridge, there are so many bridges in India. So for it now, if we have to involve a robot in this task, we need a robot which sticks to the wall, which adheres to the concrete surface. So for that, when we started our not focused especially on concrete surfaces, like magnetic adhesion systems are there, but for mostly focused on ferromagnetic surfaces or metallic surfaces. Very few researchers, thanks to very few researchers on wall climbing robots on concrete surfaces, and thanks to them we the ideal or perfect distance between the magnets, how you have to place the magnets, what would be the optimum distance, and thanks to those researchers. But very few researchers were there on this particular. So our research focuses on our approach and constraint set as it should be adaptable and scalable in the sense whatever addition mechanism we are designing, it should be able to adapt itself to any kind of robot design. It should not be like specifically you're designing a robot just for this task. No, you're having any ground mobile like mobile robot you have. So just it should in the sense it should be the design should be such a way that that everything was being tweaked. So we have to see it in all aspects. And being a mechatronics uh, graduate, our focus is mostly on from end to end design. From it should not be like focusing on just one thing. It should focus on everything. And ease of use, ease of operation, and maneuverability. And ease of operation, ease of use is understood by itself. But maneuverability, that mechanism should never be a hindrance to the robot stable and portable concrete structure in the of the so for that, if we making the robot stick to the surface. So in all the cases, it should be well aligned. The design should be in such a way that it should be very well aligned. And so the methodology which we used was that when impeller mechanism, magnet mechanism, a lot of things like that. And as I said, for ferromagnetic surfaces, they are using magnets for as well. But when this application is concerned, as you saw in the pictures, there is no chance that at some are going to provide electricity to that. If you are using an electromagnet or an impeller mechanism, for example, there's no chance that at such a great heights and you're going to provide an electricity for that, or you're going to use such a high capacity battery for that, so that it will increase the weight of the robot and it hinders the performance. Like we have to consider a lot of things for that. So for this application, we have decided to use a permanent magnet. But while using permanent magnets, there are various criteria for that too. So we need to consider about what are the different grades in permanent magnet, how well it can align itself to the surface. So based on all of that, the research was carried out. So we designed the three-dimensional model for the adhesion mechanism using a CAD software. And for magnetic simulations, for electromagnetic simulations, we used ANSYS Maxwell software. So we have chosen NDFE52 magnets. So why this particular grade magnet is because we have a lot of grades in magnets, as I said. But the one which we took, like for example, we took a standard ISO standard wall in India. Based on ISO standards, we took a wall, we took the dimensions of it. Now we needed a magnet which could, as I said, it should attract the internal steel rods. So for that, we needed a high permeability rate of that magnet. The magnetic flux should go very well inside that concrete surface. So we chose an NDFE52 magnets for that, because that was providing an optimum value which we require. For yoke material or flux concentrator, we chose iron, ferrite, permalloy, electric steel, and cobalt iron. These were the materials we chosen. Then next, we have designed this wall cement block as I said, based on Indian standards and the dimensions. We have chosen this particular wall and designed it in a CAD software. These were of addition mechanism. We will be discussing about why and which design is the best among these things. So when we started, and in this design, if you can see there are two magnets which are facing outwards as North Pole and one alone in South Pole. If you can see the X-shaped design, all the four are North Pole and the center one is South Pole. The same goes to the other one. Why this is in such way that the amount of flux entering should be greater than your holding capacity will be much more higher. So you're the four ways and coming out and attaching yourself to a single point. So that is the South Pole in the center. If you can see the X-shaped design. Environment, as I said, in this picture, the X-shaped configuration is shown. So as you can see, the magnet which we shows, NDFE52 is providing us optimum results by entering the fluxes entering. So it is passing that, and at the same time, all the flux lines, as I said, all the North Poles going in, and it is coming towards the South Pole from the center. And if you now, as I said, different designs investigated in this project. So everything. So as I said, from end to end, it should be designed well. So now keeping that in mind, by varying the dimensions of the magnet alone, like 30 by 30, 40 by 40, 50 by 50, and same goes to 50 by 50. And also by varying the number of magnets. For this test, we took 5 and 4 magnets. But we, by tweaking the purpose was that to tweak the design dimensional parameters of the magnets alone while keeping the magnet separate, we can see that the result was that the greater the length and width of the magnet, the better adhesion force was achieved. Next, when I said we use so many yoke materials, so out of in these graphs, if you can see, the higher result was achieved by cobalt iron and iron. Now the reason, although yoke material might not be significant, and the reason for choosing only these materials is that uh, it has all these materials have high permeability rate for magnetic application, which is required for electrical applications. Although these materials might not be much significant, but the bulk or weight that comes with these materials and the compromises which we have to make in the application because of choosing a particular material is very much important. That's why in this graph you can see the permeability rate is very high for yoke material. But for our application, which was iron alone, what we did was fulfilling all the approach criteria which I stated in the above slide, shows that this iron material could provide us a better result compared to all other magnets. And also one more reason is that iron is very much easily available, whereas the other materials have to be sourced in order to be used. And these graphs show the various number by varying the number of magnets and also the standoff distances. It can be understood that the more the number of magnets, the lesser the standoff distance, the better results that could be achieved. But again, if you increase the number of magnets, then the weight increases. If you decrease the number of magnets, then your payload capacity decreases. So to keep things optimal and pragmatic, a 5 magnet design, which is the X-shaped design, was chosen with a standoff distance of 2 mm. To conclude this, overall we found out that this was the perfect design for magnetic adhesion mechanism. And why is it perfect? Because as I said, the material wise, iron is easily available in the market. Second thing, the dimensions wise, studies show that the greater the dimensions, the better the adhesion mechanism, adhesion results. And uh, keeping the number of magnets optimum and also maintaining the weight parameters of the entire robot, that design was perfect. And as I said, all the approach criteria, easy to use, all those things would be met. So this mechanism, snap it up in a very short time. So we thank Royal Academy of Engineering for helping us in this research.
Okay, thank you. Does anyone has any question?
I have a question. Can you hear me?
Yes, we can hear you. Please ask.
Yeah, I was watching the different materials that you use for the yoke. Have you ever tried the new metal as a yoke?
Get you? Hello.
Yes. Did you hear my question?
Your voice was breaking in between. Can you repeat the question again, please?
Yeah, the question was regarding the different materials that you use for the yoke. Have you tried
Yes.
new metal?
Like synthesizing an entirely new metal?
Yeah, new metal as a yoke for your.
No, madam. Like entirely synthesizing a new metal for a yoke material was not done, because the one which I showed, the all 5 materials which we used, which was shown, was the new material for a wall climbing application, like for a yoke material. And why is that new? Is because these materials are and ferrite. Remaining all the materials are not available. We didn't choose like our much more focus was on designing an addition mechanism which has to be synthesized on our own, produced in a new way completely. So that was the approach which we kept. So that's why we didn't synthesize any, we didn't use any new metal in this yoke design. So that is the reason.
I was talking about the mu metal, which is a metal that has a higher relative permeability than iron, for example. So it will be the same weight as your iron, but you will be using less material because it has higher relative permeability. So you might be able to reduce the whole weight of your adhesion mechanism. That's what I was talking about. So it's just a suggestion. Maybe you can try this mu metal for CO2 research and see what you can achieve. Maybe less weight on your adhesion mechanism.
We could try that, surely. That's a new input which was being given. Thank you.
I have a question.
Yes, please.
A cost-benefit question. With your very best performing material, is it much more expensive than the worst performers, or not much difference?
Best performance material iron, then
No,
that's not very expensive.
Okay, thank you. Yes,
Yeah,
thank you.
thank you.
And I have a question also.
Yes, sir.
As I understand, this magnet should be so strong to penetrate concrete to reach, for example, metal rods. Does it affect on the electronics and sensors of the robot itself?
Yes, sir.
Because
We
it's so
also had
strong.
this. Yes, we also had this doubt. Alone will be fully immersed inside the yoke. Only the one part which you're seeing, the north face, south face, that alone will be focusing outside. So, as you said, does it affect the electronics of the robot? No, because the back side of the yoke where we placed, like we tried with this, the electronic inference was not at all observed. On the outside the yoke, behind the yoke, I'm saying, where the magnets are not even faced, since it is completely immersed inside, and the yoke, wherever the robot is, I mean the yoke addition mechanism is facing, the magnetic rays will be going on only in that, the flux lines will be going on only from that phase.
Okay, thank you.